For years, we have relied on orbiting observatories, Hubble, James Webb, and Chandra, to unveil the cosmos with clarity that ground-based instruments could never match. But now, everything has changed. A telescope still rooted to Earth, still fighting through our planet's turbulent atmosphere, has produced images so vast, so razor-sharp, and so unexpectedly profound that scientists have been left speechless. Because for the very first time, the Vera C Rubin Observatory has turned its gaze skyward, and what it captured on that inaugural night is not merely stunning, it is deeply unsettling. It offers a view of a sky so packed, so chaotic, so bursting with motion, that it threatens to dismantle everything we thought we knew about the universe. A camera the size of a compact car, snapping 3.2 billion pixels in a single frame. A single exposure vast enough to encompass 40 full moons. A flood of data so immense that generations of researchers will struggle to process it all. Yet even its earliest images already harbor astonishing secrets. Colliding galaxies, infant stars, tens of thousands of ancient star clusters, and more asteroids in a single night than humanity once found in weeks. This is the breakthrough astronomers have been awaiting. A machine powerful enough to monitor the heavens in real time, capture cosmic phenomena as they unfold, and expose structures we never dreamed existed. Tonight, we explore what the Vera Rubin Telescope has just revealed, and why its debut images have sent shockwaves through the scientific community. The machine that waited 20 years? The Vera C Rubin Observatory didn't just appear on a Chilean mountaintop one morning. It was more than 2 decades in the making, funded through a grueling combination of proposals, setbacks, and political negotiations, and finally installed, piece by piece, at an elevation of 2,682 meters on the El Peñón peak of Cerro Pachón, in the Coquimbo region of northern Chile. The site of this observatory was chosen because the air above it is almost uniquely suited to observing the sky. The Atacama Desert lies nearby, one of the driest environments on Earth. Rainfall here is almost non-existent, clouds are rare, and light pollution is essentially zero. On most nights, the atmosphere above Cerro Pachón is so stable and transparent that what you see through a telescope is close to what you would see from space. Not completely, but close enough to be revolutionary. This groundbreaking facility is named after the widely celebrated late astronomer, Vera Rubin, whose work helped reveal one of the universe's greatest mysteries. In the 1960s, Vera Rubin studied how nearly 60 galaxies rotated and uncovered something that should have been impossible. The stars at the outer edges of these galaxies were moving so fast that, based on the gravity generated by all the visible matter inside them, the galaxies should have torn themselves apart, yet they remained intact. Something unseen was holding them together. Rubin's observations provided some of the strongest evidence yet that the universe is filled with vast amounts of invisible matter, now known as dark matter. This paved the way for the establishment of the observatory, which began in a far more humble way. In the early 1990s, the idea existed only as sketches scribbled on a napkin, a bold vision for a telescope that could transform our understanding of the cosmos. Initially called the Dark Matter Telescope, the concept soon grew beyond its original mission. By 2001, it had evolved into the Large Aperture Synoptic Survey Telescope, reflecting a much grander ambition: to survey the entire night sky and uncover everything from asteroids and exploding stars to the deepest mysteries of the universe itself. Between 2001 and 2010, that ambitious dream attracted support from the United States National Science Foundation and the Department of Energy, as well as pledges from private donors, including technology billionaires Charles Simonyi and Bill Gates, totaling $30 million. What started as a simple sketch gradually became one of the most powerful astronomical projects ever attempted. At the heart of the Rubin Observatory sits the Simonyi Survey Telescope, and what makes it unusual is its design. Most large telescopes use 2 mirrors. The Simonyi survey uses 3 mirrors in a configuration called a 3-mirror anastigmat that delivers sharp, undistorted images across a field of view stretching 3.5 degrees in diameter. That means every single image the telescope captures covers an area of 9.6 square degrees of sky, more than 40 times the apparent surface area of a full moon. No other large aperture telescope on Earth does that. The primary mirror spans 8.4 meters. But the mirror alone isn't what makes Rubin extraordinary. What makes it extraordinary is what sits behind it. The LSST camera, the largest digital camera ever built. It weighs nearly 2,800 kilograms, stretches roughly 3 meters from end to end, and contains 189 individual charge-coupled device sensors, each one precisely calibrated to ensure that a star photographed at the far edge of the frame is just as sharp and accurate as one captured at the very center. The LSST camera records in 6 different wavelength bands, from ultraviolet light through visible light and into the near-infrared. And one of its 3 fused silica lenses holds the record for the largest lens ever fabricated for any astronomical instrument. Its robotic filter exchange system can swap between these wavelength bands in seconds, allowing the telescope to gather multiple types of data from the same patch of sky in a single night's work. Put it all together, and you get a machine with an 18-do, which is a measure combining light gathering ability and field of view, of 319 square meters per square degree. That is more than 3 times greater than any previous wide-field telescope ever built. The Vera C National Accelerator Laboratory assembled the camera, while the NSF Noir Lab managed the telescope and site. Watch parties were held across 6 continents on the night the first images dropped, with participants from 28 countries watching live. They had all been waiting a long time, and the telescope was finally ready to show them what it could see. The night the universe overflowed. On June 23, 2025, the Vera C Rubin Observatory released its first images to the world at a public event in Washington, D.C. Astronomers had expected something impressive, but what they got was something that made several of them stop and stare in silence. In just over 10 hours of test observations, the telescope had captured more than 10 million galaxies and Milky Way stars. It had detected over 2,000 previously unknown asteroids, including 7 classified as near-Earth objects. And it had done all of this during what was essentially a warm-up run. Not its primary mission, just preliminary tests to verify that the systems were working. The centerpiece of the first release was a mosaic built from 1,185 individual exposures, a sweeping portrait of part of the southern Virgo cluster, the nearest large galaxy cluster to the Milky Way. The resulting image was nicknamed the Cosmic Treasure Chest almost immediately, and looking at it, it is easy to understand why. Spiral galaxies stretch their arms lazily through the frame. 3 separate galaxy mergers are caught mid-collision, their shapes distorted by gravitational forces pulling billions of stars off their original paths. Faint filaments, the cosmic web, threads of dark matter and gas connecting clusters across vast distances, are visible at the edges. In the background, if you zoom all the way in, you find a sea of faint reddish objects, each one a galaxy so distant, its light has been shifted toward the red end of the spectrum by the expansion of the universe itself. That entire mosaic, extraordinary as it is, represents just 0.05% of what Rubin will eventually detect. Over 10 years, the observatory is expected to capture approximately 20 billion galaxies. The Cosmic Treasure Chest was a preview, a single frame from a film that will take a decade to complete. Beyond their aesthetic value, these truly stunning images represented a monumental step forward in astronomy, signaling the commencement of the 10-year-long legacy survey of space and time. The second major release was a mosaic of the Trifid and Lagoon nebulae, 2 star-forming regions located several thousand light-years away in the constellation Sagittarius. This image was built from 678 separate exposures, taken over roughly 7 hours of observing time. What it showed was not what people expected. The Lagoon Nebula, which spans 55 light-years, occupied only a portion of the frame. Surrounding it in the same image were open star clusters, the glowing Trifid Nebula, the dense globular cluster NGC6544, and dozens of other objects at wildly different distances. There were some newborn stellar nurseries and some ancient star groups that formed billions of years earlier. Rubin captured all of them in one image, simultaneously, without any of them losing sharpness. To understand what that means, consider this. A single image from the LSST camera is so detailed that displaying it at full resolution would require 400 ultra-high definition television screens arranged together. If you printed one image at standard resolution on standard paper, it would cover the area of a basketball court filled with those same screens. The data in each photograph is not just visual. It contains layers of spectral information, chemical signatures, motion trails of moving objects, and thermal data across 6 wavelength bands that the human eye cannot see. Within hours of the images going public, researchers were reporting discoveries. An unusually large and rapidly rotating asteroid in the main belt, later designated 2025 MN45, was identified in the test data. Scientists at the Max Planck Institute noted that the galaxy images already contained hints of supermassive black holes in galaxies so young they shouldn't have had time to grow that large. These were objects described by one researcher as like discovering a full-grown adult in a kindergarten class. What the first images showed was stunning. What the telescope is actually designed to do goes far beyond that. The machine that watches everything at once. Most telescopes are built to look at one thing. They point at a galaxy, study it for hours or days, collect their data, and then move on to the next target. That is how astronomy has worked for centuries, and it has produced extraordinary science, but it has also left enormous gaps. The Rubin Observatory was designed to eliminate those gaps. Its mission, starting in late 2025, is called the Legacy Survey of Space and Time, LSST for short. And the concept behind it is simple to state, but staggering in its implications. Every 3 to 4 nights, Rubin will scan the entire visible southern sky. Not just some selected regions or interesting targets, but all of it. To complete that scan, the telescope will take approximately 1,000 images per night. The automated systems that control it will move it from position to position with mechanical precision, capturing each patch of sky for roughly 30 seconds before repositioning. The resulting data, around 20 terabytes every night, will be transmitted via a dedicated 100 gigabit per second fiber optic connection directly from Chile to the Rubin Observatory's United States data facility at the SLAC National Accelerator Laboratory in California. From there, an automated processing pipeline calibrates the images, corrects for atmospheric distortions, identifies moving objects, flags transient events, and integrates everything into a continuously updated map of the southern sky. All of this happens before a single scientist looks at a single image. By the end of the 10-year survey, Rubin is expected to have cataloged approximately 40 billion individual stars, galaxies, and other celestial objects. The total data volume will approach 500 petabytes. That is more data than all other optical observatories in history have produced combined, just from one telescope, in 1 decade. What makes this genuinely new is the time dimension. The National Science Foundation describes it this way. Where astronomy has mostly given us snapshots, Rubin will give us a movie. Every 3 nights, the same patch of sky is imaged again. The computer systems compare each new image to the previous ones from the same location. And anything that has changed, that is, anything that has appeared, disappeared, brightened, dimmed, or moved, gets flagged automatically. And an alert is sent out to scientists worldwide within 60 seconds. Supernovae that would once have gone unnoticed until they were already fading will now be captured the moment they ignite. A variable star that pulses on a 3-day cycle will be caught mid-pulse. An asteroid following an unusual trajectory will be tracked from its first detection onward. And any interstellar visitor that enters the solar system on a trajectory no known object should follow will be identified with enough lead time actually to study it. It is also predicted that Rubin could detect thousands of so-called failed star brown dwarfs within the Milky Way. These celestial bodies with masses between 13 and 80 times that of Jupiter, 0.0, 13 to 0.0, 8 times the mass of the Sun, are thought to form like stars, but fail to gather enough material to reach the mass needed to trigger the nuclear fusion of hydrogen to helium, the process that defines a main sequence star in their cores. This makes them extremely faint and elusive, but also extremely important for understanding how stellar bodies form and evolve. The NSF has stated plainly that the data gathered by Rubin in its first year alone will exceed the total collected by all other optical observatories combined. Astronomers call this discovery space the range of events and objects an instrument can detect, and Rubin's discovery space is larger than anything that has come before. But detection is only half the story. What Rubin was really built to chase, the thing its designers wanted a above everything else, has been invisible to human instruments since the beginning of science. The hunt for what we cannot see. The telescope named for Vera C. Rubin was meant to hunt for what she spent her life researching. Galaxies, by every known law of physics, should rotate the way our solar system does. Objects closer to the center orbit faster, while objects at the edges orbit more slowly. That is how gravity works when mass is concentrated in one place. But when Rubin and her collaborator, W. Kent Ford, measured the rotation curves of dozens of spiral galaxies, they found that the stars at the edges were moving just as fast as the stars near the core, sometimes even faster. Also, the rotation curves were flat where they should have been declining. The only explanation that worked was one that nobody wanted. There had to be more mass than what was visible. A vast amount of mass, distributed in a halo around each galaxy and invisible to every instrument available, exerts a gravitational force on the stars without emitting a single photon of light. Rubin called it dark matter. And while she was not the first to suggest such a thing existed, she provided the first clear, systematic, observational evidence that it was real. Dark matter is not a theoretical placeholder, but an actual component of the universe. Today, scientists estimate that dark matter makes up roughly 27% of the total mass energy content of the universe. The ordinary matter that makes up stars, planets, gas, dust, literally everything you have ever seen or touched, represents only about 5%. The remaining 68% is something else again. It is called dark energy, a force or property of space-time itself that appears to be driving galaxies apart at an accelerating rate, overcoming gravity on the largest scales. Dark matter and dark energy together account for 95% of everything that exists, and neither one has been directly detected by any instrument ever built. This is what the Rubin Observatory was originally conceived to address. From its predecessor concept till now, the approach has been indirect but powerful. By mapping how billions of galaxies are distributed across space, and by measuring the subtle distortions in galaxy shapes caused by gravitational lensing, dark matter bending light from objects behind it, Rubin's data will allow scientists to construct the most detailed map of dark matter's distribution in the universe ever assembled. On the dark energy side, Rubin will track the expansion history of the universe by observing millions of Type 1a supernovae, which are stellar explosions of known brightness used as cosmic measuring sticks, and by watching how the large-scale structure of galaxy clusters has changed over billions of years. The goal is to determine whether dark energy is constant, as Einstein's cosmological constant would suggest, or varies over time. That distinction matters because if dark energy is not constant, the universe is not behaving as our best theories predict it should. The answers, if the Rubin Observatory finds them, will reshape fundamental physics. They will not come quickly or easily, but no instrument before this one has been capable of gathering data at the scale required to attempt the measurement. 2,000 asteroids in 10 hours. In the first 10 hours of test observations, before the official mission had even begun, Rubin identified 2,104 previously unknown asteroids. 7 of them were classified as near-Earth objects, rocks whose orbits bring them close enough to Earth's orbital path to be worth watching. To appreciate what that number means, consider the scale of the problem. The worldwide network of asteroid hunting telescopes currently detects approximately 20,000 asteroids per year, all of them combined. Rubin, during a single night of test observations not even specifically designed for asteroid detection, found more than 1/10 of that annual total before breakfast. Over the full 10-year survey, the Rubin Observatory is expected to discover and track several million asteroids, including approximately 100,000 near-Earth objects. That would roughly triple the number of cataloged near-Earth objects currently known. For objects that pose a potential impact risk, earlier detection means longer warning times and more response options. The difference between discovering a threatening asteroid a decade before impact versus 2 years before is the difference between having options and having almost none. An unusual early discovery from the test data was the asteroid designated 2025 MN45, identified in the main belt. It was notable for its unusually large size relative to its rotation rate. It was spinning faster than most objects of comparable mass, a finding that added new data to open questions about how asteroids form and evolve. But asteroids are not the only fast-moving objects that Rubin is positioned to detect. The telescope's wide field of view and rapid 3 to 4 day scanning cycle also make it, by a significant margin, the most capable tool humanity has ever had for detecting interstellar visitors, objects that enter the solar system from outside it on trajectories that no solar system object could naturally follow. We have detected 2 such objects before. The first, a dark red elongated body called 1I/Oumuamua, was spotted in 2017 on its way out of the solar system. Its unusual shape, acceleration, and the absence of any visible outgassing remain unexplained. The second, 2I/Borisov, appeared in 2019 and behaved more conventionally. It was a comet-like object with a visible tail, probably composed of ice and rock from another star system. Astronomers had weeks to study both of them before they became too faint to observe, and in both cases, the objects had already passed closest approach to the Sun before they were found. Rubin's rapid cadence means an interstellar visitor will be detected far earlier in its trajectory, potentially giving researchers months rather than weeks to observe it at close range. Over the next 10 years, astronomers estimate that Rubin may detect dozens of such objects. Each one is a sample of material from another solar system, chemistry formed around an alien star, shaped by conditions we cannot directly observe. Every interstellar visitor Rubin catches is, in a real sense, a message from somewhere else. Asteroids and visitors from other stars are things we can track and measure. What Rubin will attempt next involves mapping the universe's own skeleton, a structure so ancient, so vast, and so faint that until now, no instrument could see it at all. Cartography of the Milky Way. Mapping our own galaxy is harder than it sounds. From our position inside it, roughly 26,000 light-years from the center, the Milky Way is a disk of hundreds of billions of stars, so densely packed in certain directions that we cannot see through them. The outer edges of the galactic halo, the vast, diffuse sphere of stars, gas, and dark matter that surrounds the disk, are so remote and so sparsely populated that finding individual stars there requires an instrument with enormous light-gathering ability and a very wide field of view. The Rubin Observatory has both, and the stars it will use to map the halo are a specific type called RR Lyrae, which are ancient pulsating variables, hundreds of millions of years old, that swell and contract in cycles lasting between 7 and 11 hours. What makes them useful is not their age, but their predictability. An RR Lyrae star's cycle period is directly related to its luminosity, meaning if you know how fast it pulses, you know how intrinsically bright it is. Compare that to how bright it appears in your image, and you can calculate its distance with remarkable precision, even across tens of thousands of light years. In Rubin's first test images, researchers identified 46 RR Lyrae stars. That number alone was not surprising. What was notable was where they were, in the outer halo, far beyond the main disk of the Milky Way. By the end of the 10-year survey, scientists expect to have cataloged approximately 100,000 of them, scattered across a volume of space that no previous survey has sampled at this depth. What that data will reveal is the three-dimensional architecture of the Milky Way's outer reaches. Stars at the edge of the halo did not form there in most cases. They were pulled there. Ancient collisions with smaller dwarf galaxies left tidal streams behind them, rivers of stars stretched across tens of thousands of light years that still trace the orbital paths of galaxies the Milky Way consumed long ago. The Sagittarius stream is the most famous of these, a loop of stars stripped from the Sagittarius dwarf galaxy, over billions of years of repeated close encounters. But there are others, fainter, harder to find, and each one carries chemical information in its stars that can tell us when and how that collision happened. Rubin will find them, and by mapping their positions with enough precision to trace them back to their sources, astronomers will reconstruct the merger history of the Milky Way, a geological record of cosmic collisions written in the positions of stars so faint that previous instruments could barely detect them. There are also structures in the halo that do not fit neatly into any known category. Overdensities of stars with no obvious origin, gaps in the distribution of stream stars that suggest encounters with invisible clumps of dark matter, and what may be the remnants of globular clusters dissolved long ago. Rubin's combination of depth, width, and repeated scanning makes it, for the first time, capable of systematically mapping all of these features simultaneously. The The survey will also catalog approximately 17 billion individual stars across the Milky Way and nearby galaxies. 17 billion data points, each one a position, a brightness in 6 wavelength bands, a history of how it changed over 10 years. It is more information about the structure of our galaxy than has been gathered in all of human history combined. Rubin will see deeper, wider, and longer than any ground-based instrument before it. But none of that matters if the data stays locked in a server room in California. Who gets to look? One of the quieter revolutions embedded inside the Rubin Observatory's design is what happens to the data after it is collected. The answer, in short, is that it goes to everyone. The observatory's public platform, Sky Viewer, is already available. It is not a simplified illustration or a curated set of highlights. It is the actual data at full resolution, accessible through a browser. A user can zoom from a wide view of 10 million galaxies down to the level of individual stars in a matter of clicks. The entire cosmic treasure chest mosaic, stitched from over 1,000 exposures, can be navigated as you would a digital map. At full zoom, previously unseen detail appears. Individual galaxy arms, tidal streams between merging clusters, point-like objects that, on closer inspection, turn out to be distant galaxy clusters that have never been cataloged. This is not a small thing. Until recently, data at this scale and resolution existed only within the computing infrastructure of professional observatories, accessible only to researchers with the right credentials and hardware. Rubin makes it publicly available. The scientific team has explicitly invited citizen scientists to participate, noting that the volume of data arriving nightly will be too large for professional astronomers to examine in detail alone. The expectation is that some genuine discoveries, faint comets, unusual variables, and anomalous objects will be first noticed by someone browsing the public archive from their living room. The data pipeline behind this system is itself a significant engineering achievement. 20 terabytes arrive every night, and within 60 seconds of each new image being processed, automated alerts go out to the global scientific community describing any changes. Those alerts are made available to anyone who registers to receive them, whether it's a small observatory in Chile, a university in Nigeria, or a researcher in India. All receive the same alert at the same time as the largest institutions in the United States. The NSF made a deliberate choice in designing Rubin's data policy. No proprietary period, no institutional priority queue. The first year of data alone will exceed, in volume and coverage, everything gathered by all other optical telescopes in history combined. And all of it will be publicly accessible. By the end of the survey, 500 petabytes of data will exist. It will take generations to analyze these fully. The discoveries that are already in that data, in the images from the first 10 hours, outnumber what any single research team could examine in a decade. Hidden inside those files, invisible until someone thinks to look at the right coordinates with the right question, are things nobody has seen yet. The universe has always been this complex, this dense, this alive with motion, collision, and transformation. Rubin did not create any of it. What it did was give us for the first time an instrument fast enough, wide enough, and deep enough to see all of it at once. Not a snapshot, but a full-blown movie of the cosmos. And the movie has barely started. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.